In the last video, we introduced the intensity reflection coefficient. In this video, we're going to be looking at a couple of examples to better understand what this is about. The first example comes from May-June 2024 question paper 4.2. Again, as always, I highly encourage that you write notes of all these materials that we're covering. I highly encourage that you solve these problems on your own, because that's the only way you can learn, right? If you just regurgitate and just consume all the information that I'm giving you, you're never going to really learn this material, right? It's not going to be very helpful if you're just copying these examples word for word. Try them on your own. If you're stuck, then come back and see the first step that you need. Don't look at the other steps. Try to figure out where you went wrong and try to fix that, right? You can. No one is going to control you. You can look at the examples. You can just write these things. But unless you're able to understand how to solve these problems, you're never really going to learn a lot, right? So I highly encourage that you really pay attention and you really gain a lot from these videos. Okay, so table 10.1 shows some data for water and for glass. So you have the density of water and the speed of sound, the density of glass and the speed of sound in glass. And we've been asked to determine the intensity reflection coefficient that is incident, so the intensity reflection coefficient for ultrasound that is incident on a water glass boundary. So essentially, if I've been asked for such a calculation, what's important is to essentially say the intensity reflection coefficient alpha is gonna be, so alpha is gonna be equivalent to Z2 subtract Z1 squared divided by Z2 plus Z1 squared, right? Or Z2 minus Z1 over Z2 plus Z1 squared. All of that together squared. Okay. Then the first one that we need is to find the Z for water, then to find the Z for glass, essentially. Okay. So the Z for water is going to be equal to 1,000 times 1,420. 1,000 times 1,420. And that's going to give you an answer of 1.42 times 10 to the power of 6. Okay. 1.42 times 10 to the power of 6. Then the Z for glass. Okay. Then the Z for glass, that's going to be equal to 2,500 times 4,560. So that's equal to 2,500 times 4,560. 4,560. That's going to be equivalent to 11.4 times 10 to the power of 6. 11.4 times 10 to the power of 6. So essentially, my value for alpha is going to be 1.42 times 10 to the power of 6. Subtract 11.4 times 10 to the power of 6. All of that squared. Divided by 1.42 times 10 to the power of 6 plus 11.42. Sorry, now I think I'm just getting a bit carried away here. 11.4 times 10 to the power of 6. All of that squared. And the value of alpha that I'm going to get from this computation is essentially going to be 0.61. 0.61. Okay. So this is how I'm applying and finding the intensity reflection coefficient. And what does this number mean? What does this number tell me? Okay, what does 0.61 tell me? It tells me if this is, okay, what mediums am I comparing here? Water and glass, okay. If this is glass, and if this is water, and I have an incident wave like this, let's just say I, this is the intensity of the incident wave, then 0.61 of I is going to get reflected. Okay? And 0.39 of I is going to get transmitted. Okay, that's what I mean by saying I have an incident wave, which is I. Some of it is going to get reflected, then some of it is going to get transmitted. And then the relationship between all of that is that they must add up to 1. So if 0.61 of I is going to get reflected, then 0.39 of I is going to get transmitted. Okay. If we now look at 9702 M23 question paper 42, we want to better understand this example. Again, we're just trying to solve a couple of examples to help you better understand the intensity reflection coefficient. So we've been asked to determine the units for the specific acoustic impedance values that are shown in table 9.1. So essentially, if you have the density, which is 1.30, and you have the speed of ultrasound, which is 330, the goal is to find the specific acoustic impedance. So Z is going to be equal to, density multiplied by the speed of sound. And your goal is to find the specific acoustic impedance, the units themselves rather. Okay, so the units of density are kg, m to the power of -3. The units for sound are ms to the power of -1. So this is going to give you kg, m to the power of -2, s to the power of -1. And this become the units for specific acoustic impedance. So it's going to be kg, m to the power of -2, s to the power of -1. And that's going to give you the units that you need. Okay. The next example, use the data from table 9.1 to explain why ultrasound cannot be used to produce an image inside air-filled cavity such as lungs. Okay, I'm given these specific acoustic impedances, specific acoustic impedance for air, specific acoustic impedance for soft tissue. Okay, so we've been asked to calculate or to explain why ultrasound cannot be used to produce an image inside an air-filled cavity such as the lung. So if you look at the structure of the lung, it contains air inside, right? And then there's soft tissue on the outer exterior. So the goal essentially is saying, is it very difficult to produce an image of the inside of the lung? It's going to be very difficult because the air and soft tissue have different acoustic impedances. So if you ever reach a soft tissue air boundary, most of the waves are going to be reflected back, and they're never going to pass through to soft tissue, so that we can be able to really see the image that is present. And I can quantify this because I can look at alpha and say alpha is equal to 4.3 times 10 to the power of 2 subtract 1.7 times 10 to the power of 6 all over 4.3 times 10 to the power of 2 plus 1.7 times 10 to the power of 6, and then all of that squared, and that's going to give you a value of 0.99, or approximately 1, actually, or approximately equal to 1. So what this tells me is that since the intensity reflection coefficient is very close to 1, most of the ultrasound is going to be reflected, and very few of it will actually be transmitted. So if you have lungs, you can't really see the other end of the lungs. It's going to be very difficult for you to really view and image the lungs themselves, because there's always going to be a confusion whenever you reach an air soft tissue boundary, because there's so much specific differences in the specific acoustic impedances. So this is sort of an application question where you can be able to use that. Or you can be asked, describe qualitatively, that's October, November 2021, describe qualitatively how the specific acoustic impedances of two materials affect the intensity reflection coefficient at the boundary between the material. Okay, so we can therefore say the differences in specific acoustic impedance will affect IRC, the intensity reflection coefficient. Okay? If the difference is similar, the IRC, if the differences are very, very similar, the IRC will be close to 0 or very low. And if it is very large, the IRC will be close to 1. Okay, I hope that makes sense. So the differences in the acoustic impedances affect the intensity reflection coefficient by utilizing that equation. So if the IRC is close to 0, that implies the differences is very, very similar. Then if the IRC is very, very large, or it's nearly close to 1, that implies that the difference between the acoustic impedances is also very, very small. Is also very, very large, sorry. The last one, by reference to specific acoustic impedances, explain why there's very little transmission of ultrasound from air to skin. Actually, the second from last one, rather. Okay, so why is there little transmission of ultrasound from air into skin? We already know that for a fact that air is going to have a lower specific acoustic impedance than skin because of the differences in density. So we can therefore effectively just say there is a difference. Okay, there's a difference in specific acoustic impedances of air and skin, so we can say Z of skin is actually greater than Z of air. Okay, but the IRC depends on the specific acoustic impedance. I'm a bit lazy, so I'm going to say SAI, but it depends on that. So since the IRC is very high, due to the differences in Z, most of the wave is reflected, hence very little will be transmitted. Okay. That's essentially it. Because there's a difference in the values of Z. The IRC depends on the values of Z, so it's going to be very high. So most of the wave is reflected, therefore very little will be transmitted when moving between air and skin. Our very, very last example. A parallel beam of ultrasound, I0, is incident normally on the boundary between two media. The media has specific acoustic impedances Z1 and Z2. The intensity of the ultrasound beam that is transmitted across the boundary. So whatever makes through is IT. That implies whatever goes back over here is IR. Okay. Explain the significance of the magnitude of Z1 and Z2 on the ratio IT over I0. Okay. So if Z1 and Z2 are equal, if Z1 and Z2 are nearly equal, IR will be small. Okay? And we know for a fact that if IR is essentially very small, IT is going to be higher. Because if very little is reflected, IT will be very higher. So if they're nearly equal, hence IT over I0, IT over I0 will be close to 1 or very high. Okay? That implies the ratio of the amount of wave that is being transmitted over the incident is going to be very high. And then, if Z1 and Z2 are very different, then IR will be large, so IT over I0 will be close to 0. Okay, that's essentially it, guys. We're sort of comparing the magnitudes of Z1 and Z2 and how they're related to IT, essentially the transmitted intensity. Again, you can always try to solve other questions. I have a particular document that I've created for you guys, worksheets that I've created for you to solve. You can always, again, refer to this at any given time, solve most of these problems to really see if you've understood this concept. It's very, very important for you to be able to do that. And again, thank you guys for watching, and I'll see you guys in the next video, where we'll be talking about the coupling medium.